Predictive power is critical in science, and for chemists, you have to start with the ability to predict whether or not a reaction is going to take place. And then you worry about what the products of that reaction might be. And after that, you start to worry about amounts, how much reactant will make how much product. And that's the basis of stoichiometry. In stoichiometry, you're taking a look at the balanced chemical equation to come up with mole ratios relating the reactants to the products. And you'll see why you have to end up using mole ratios instead of masses. But moles happen to be proportional to things like concentration and pressures and even volumes for gases and things like that. So it becomes fairly versatile. Stoichiometry looks scary because it's applied chemistry and you have chemical reactions. But one of the things that I like to emphasize is the idea that the mathematical difficulty in stoichiometry is a strictly psychological hurdle. So if we were to talk to someone about recipes and cooking, everybody can understand how it works. If you have something as simple as making a pitcher of Kool-Aid, 2 quarts of water, 1 cup of sugar, 1 packet of Kool-Aid, you've got a pitcher full of Kool-Aid. And if somebody said to you, oh, you need to make enough Kool-Aid to fill 3 pitchers or whatever, you'd say, okay, well, I've got to multiply everything by 3. And that's the basis there, is you are scaling a recipe. You multiply your 2 quarts of water by 3, you get 6 quarts of water. You multiply your 1 packet of Kool-Aid by 3, that's 3 packets of Kool-Aid. Multiply your 1 cup of sugar by 3, and you have 3 cups of sugar. Scaling a recipe, and that's exactly what stoichiometry is. And so what I like to do is start out by something that's not chemistry at all, and then work my way up. So this video may seem the most pointless, but it is the most critical because it takes math that's ridiculously easy and it builds the process by which these calculations are going to take place. So let's give it a try. So an example I use in my class is some made-up scenario where we have a bicycle factory and bicycles are shipped in unassembled and you have wheels not attached to everything else. So we'll say that in this factory we have 2 wheels and 1 frame making 1 bike. So this is our general relationship. Here's our recipe, here's what we're making, and now we can come up with different numbers. And the different numbers would be based on, like, if we had a certain number of wheels, how many frames would we make, or would we need, and how many bikes can we make? Or given a certain number of frames, how many wheels do we need? How many bikes could we make? Or if we need a certain number of bikes, how many wheels and how many frames are required? And again, the math isn't what we're looking at here. We're looking at the process, the dimensional analysis idea of stoichiometry. So if we look at a first example here, where maybe we're given 400 wheels. The only 2 things we could be worried about here are frames and bikes. And so the first thing we might ask is the number of frames needed. And I think if you look at that for a moment, you need half as many frames. So the math becomes irrelevant. It's like, 400 wheels, that's 200 frames. So there's our guess in advance. And anybody can do that math. The math is not the point. The second thing we might ask is the number of bikes possible. All right, and it's a 2-to-1 ratio. Like, anybody can look at that and say, oh, those 400 wheels, I can make 200 bikes. And it's not a coincidence that these numbers are the same. But we're going to ignore them because they're not our matter of interest right now. Our matter of interest right now is the dimensional analysis behind this. So we'll make some room right here. And this is how we're going to set up every single one of these problems, regardless of whether it's bikes or not. Start with what's given. In this case, we're given 400 wheels. Okay. In dimensional analysis, the units guide the calculations. Our units right here are wheels. Okay. So the first thing is what's given, wheels. And then we want to make wheels go away and find out about the things of interest. In this case, frames are of interest, and our ratio is right here, 2 wheels. I want wheels to go away. Wheels is going to appear diagonally down. There's 2 wheels, right, for every 1 frame. So I want to know about frames. This ratio, this 2-to-1 ratio, is going to tell us the answer. And as you look at it, it's pretty straightforward. 400 over 2 is 200 frames needed. All right, so if you have 400 wheels, you're going to need 200 frames, and then we're going to make some number of bikes, and that's what we've got. So there's our part A. And just as a quick note, wheels cancel out. Everything after the first box comes from our balanced chemical equation. Okay? Everything after the first box is a ratio that's based on our chemical equation. All right, so we've got that. And hey, it was the number we guessed before. But I'm not worried about the number. I'm worried about setting this up as a dimensional analysis problem. So I need to make a bit of room there. We'll try the part about our number of bikes possible. And I want to look at this a couple different ways. Start with what's given. 400 wheels. All right, that's what we were given. We want wheels to go away so we can find out about the other things. I know, the same as I did before, that there are 2 wheels for every, in this case, I want to know about bikes. And this is the number of bikes right there. So this 1 bike is what's going to go right there because it's 2 wheels for every 1 bike. So I've got 1 bike. All right, so 400 over 2, that's 200 bikes possible. Right, and there is our answer to part B. Okay, and that was the number we had predicted before. And no surprise there. The key here, dimensional analysis, ignoring whatever is going on. When you talk to math teachers, one of the things you find out is the biggest hurdle for students is often word problems, right? They do 2 through 200 even of some multiplication process. But as soon as you take that and turn it into words, you change the context, which creates this artificial hurdle. Well, the same is true here. Anybody can scale recipes, right? But as soon as you call it chemistry, it seems like it's impossible. And again, that's why we're going to look at this the dumbest way possible, which is working with wheels and frames. And we're just going to change the words. We're not even going to change the numbers very much. And the process is all of a sudden going to seem much harder. It's not. That's the important part. So we're working on a process. This is developing this process. We got to have our balanced chemical equation every single time. Okay, and we'll work in here another idea after this example, and that idea is like comparing what we actually get to what we could have gotten. And we'll see how that goes. But for right now, let's just say we get in an order, like this is our factory. We get in an order for like 1,200 bikes. So we need 1,200 bikes. All right, so you need to put in requisition for however number of wheels and frames. So number of wheels needed, right? And spoiler alert, that's 2,400, right? And we need to know the number of frames needed, right? We want to build 1,200 bikes, and guess what? We're going to need 1,200 frames. I don't care about those numbers. That's why I put them right there. And I think it's important that everybody realizes the math is really dumb, okay? Anybody can do it. You're not impressing anyone. It's the process we're learning, so that when we change the context, it becomes less intimidating. So we're going to start out with what's given, 1,200 bikes. All right? So the same thing, the way I set this up, start with what's given. Everything after that comes from our balanced equation. Oh, here's bikes. Here's bikes. You're just matching a picture. Here's bikes. Here's bikes. This number is how many I have. 1 bike, right? And you're going to notice right here that my work is going to look exactly the same. 1,200 bikes. And I know for 1 bike, but the 2 things that I'm interested in here are the wheels. So I'm going to look over there. Ah, yeah, look. 2 wheels, and there's our ratio. Our ratio comes from the balanced chemical equation. For the bikes, I've got 1 frame, right? So bikes are gone. Now I've got wheels. In this case, 1,200 times 2 is 2,400 wheels. And over here, we've got 1,200 frames. All right, there's our answer to part B. There's our answer to part A. And that's all there is to it. I want to sneak in one other idea here. We'll call it part C. And part C is find the percent yield, right? And we'll have to define that term in a minute, but it would be a good idea, like if you did own this bicycle factory and you did have 2,400 wheels and you did have 1,200 frames, how many bikes actually get built? And that's based more in reality. So find the percent yield if you were able to ship out some number of bikes. And let's just say we can ship out 600 bikes. All right. And our percent yield is just a ratio, right? A ratio of how many things you could have made, which in this case was 1,200 bikes, to the number of things we actually made, which is 600 bikes. And so we'll work in some vocabulary as we go, but let's look at this calculation, our percent yield, which is just a ratio. And the terminology we're going to use here is going to carry over to the chemistry. It's a ratio of the actual yield to the to the theoretical yield. All right, ratio of the actual yield to the theoretical yield as a percent. All right, so very quickly doing this calculation, our percent yield in this case is going to be our actual yield. They actually made 600 bikes. Theoretically, given these amounts, we could have made 1,200 bikes, and then we turn it into a percent, and we end up with, in this case, a 50% yield. All right, and we won't get into the economics, but 50% yield is probably not adequate for a successful factory here. So scenario number one, we're going to have some amount of a reactant. We can find out the amount of the other reactant and predict how much product we can make. Scenario number two here, we're given some amount of a product, and then we can predict how much of each reactant we're going to need. Now in the big picture, there's more to it, but for right now, let's change the context and see how that goes. Our basic idea that I don't want to change is that the first box contains what's given. Every box after that in the dimensional analysis comes from the balanced chemical equation. It's a ratio. So a common reaction, or a simple reaction for us to work with, is when you have hydrogen and oxygen, all right? Two hydrogen and oxygen gas giving you water vapor or whatever, right? It looks scary, all right? Like anybody can look and say, oh, bicycle frame, bicycle wheel. As soon as you see hydrogen gas and oxygen gas, context is totally different. Everything gets flushed down the toilet and you have to start from scratch mentally. No, you don't. We have a process. Start with what's given, use the coefficients in the chemical equation as a ratio to get where we need to go. So in this case, let's just say, given 10 moles of hydrogen, we'll ask about our other reactant, how much oxygen is needed, all right, to completely react with that, and how much water can be produced or may be produced. And that's theoretical, right? Okay. So first step, you walk up to somebody on the street and hand them this and they have no idea what to do. We don't have that problem because we have a process in place. And that process says start with what's given, 10 moles of hydrogen. So in this case, we have 10 moles of hydrogen, all right? Everything after the first box is supposed to come from the balanced chemical equation. So I look at the equation, and right here, we have 2 with our hydrogen. So we have 2 moles of hydrogen, right? And what do I want to know about? I want to know about the oxygen. So again, from our balanced chemical equation, we have 1 mole of oxygen. So there's 1 mole of oxygen. The moles of hydrogen cancel out. You have moles of oxygen. Takes 5 moles of oxygen, okay? And that's our part A in this problem. And again, had it been wheels and frames, most people would look at it and know it. As soon as it's hydrogen and oxygen, people shut down, but you don't have to. It's the same process. Start with what's given, use the coefficients as a ratio when you're doing the actual calculation. So we'll do that again and say we've got 10 moles of hydrogen. And for every 2 moles of hydrogen, now I want to know about the water. There's 2 moles of water. So we cancel out, we've got moles of hydrogen, and we end up with 10 moles of water that are possible. Right? This is what's possible And another term for that would be theoretical, right? And that's coming into our percent yield calculation. So let's label this as part B, maybe sneak in over here a question, part C, okay? So we'll say if 8 moles of water maybe are actually collected in lab, find the percent yield, right? So we calculated percent yield before. Percent yield was supposed to be the actual yield over the theoretical yield times 100, all right? And I don't say times 100% even though it's true, because often people will try and punch in 100 and then punch the percent key on the calculator. And I don't know what the percent key does, and I don't think that I'm going to waste any brain power trying to figure it out. So our actual yield, it has to be given, right? And in this case, this is what was actually collected, right? And down here, this is what we could have made theoretically, right? So our percent yield is going to be that 8 moles of H2O over 10 moles of H2O times 100, or 80% yield. And that's for the reaction overall, and that comes up later in some types of calculations. A few things to consider. Some reactions don't go to completion. A lot of organic reactions for like pharmaceutical companies, maybe you get like a 3% yield. And if you can be the person who optimizes that to like a 3.5% yield, that may be like millions of dollars in profit. And you can look at that with later calculations in terms of equilibrium constants and kinetics and things like that. 80% yield is pretty unreasonable for this reaction. You should get 100% yield. But how are you going to catch your product? Did somebody screw up in lab? And that's something we should consider as well. In practice, you couldn't get over 100% yield. Like the law of conservation of mass says that's not going to happen. But as I tell my students, like somebody could screw up in lab, right? Like somebody drops your product on the floor and then sweeps it up with a bunch of dust, and all of a sudden you've gotten more product than you theoretically could have. So is it possible to get over 100% yield? No. Is it possible to calculate over 100% yield? Yes, and that means somebody screwed up somewhere. All right? So let's look at one more example here, and we'll go into more detail in the next video. For right now, our key idea is looking at one reactant or the product and then turning that into an amount of the other reactant, or turning a product into amounts of the reactants. So we'll say given, and it doesn't really matter, we'll just say like 20 moles of H2O, okay? So the first thing that I might ask is the amount, the starting amount of hydrogen. And obviously the other one may be a starting amount of oxygen, all right? And then if we're going to come up with a percent yield, right? Let's say if there are 15 moles of H2O collected in lab. And what we're saying is like somebody does this experiment in the laboratory and then they measure this amount of product. So if you get 15 moles of water collected in the lab, find the percent yield. Okay? So with this 20 moles of water, we're just going to say that was our goal. And so we used this recipe that we're going to come up with, but this is what we actually got. So that's the breakdown of this problem. We'll start with what's given, right? Our process, regardless of whether this is chemistry or building bicycles, start with what's given, use the ratios to come up with what you need. And we can kind of cut a corner here, but I guess I'll save that for another example. Start with what's given, 20 moles of H2O, right? And I want to find out about the hydrogen. I know about the H2O, 2 moles of H2O for every 2 moles of hydrogen, right? It's a 1-to-1 ratio, moles of water cancels out, and we have 20 moles of hydrogen needed, all right? And that's our answer to part A. Setting up part B, we've got our initial amount, 20 moles of H2O again. For every 2 moles of H2O, everything after that first box comes from the balanced chemical equation. We've got 1 mole of oxygen, right? So we cut that in half, and it says that we need 10 moles of O2 for this reaction, all right? Which leaves us with our third question, our percent yield. And our percent yield was supposed to be our actual yield, right? This is what somebody actually got, divided by our theoretical yield, which is our target, our goal, times 100, all right? In this particular case, we had 15 moles of water and 20 moles of water, which gives us a 75% yield. All right, we are scaling recipes. Our recipe is the balanced chemical equation. In the next video, we'll look at what to do when you don't have just an amount of one thing, but what happens if you have different amounts, like instead of 20 moles of water as a target, let's say you're given 10 moles of hydrogen and 10 moles of oxygen. How much water can you make? And then we'll continue to build on that to get a comprehensive idea of what goes on with stoichiometry.